Hi guys and welcome to this session by Intellipaat. We all know how popular containers have become in today's world. Most of the companies today have moved on from the traditional deployment using VMs to containers. Hence, it's high time that we learn about container and container orchestrating tools. So keeping that in mind, we have come up with this hands-on session today on Kubernetes, which is a container orchestrating tool. But before we get into all of that, please subscribe to our channel to never miss an update from Intellipaat. Also guys, we do provide end-to-end training on Kubernetes, so if you're interested, you can check out the course details given in the description below. Now, let's talk about today's session.
Now let's talk about the brief history. So in this section of our module, we'll be talking about how things were before containers even arrived and how throughout the history we have been deploying things and how we actually came about using containers altogether. And then we can move on and talk about this container orchestration tool that is Kubernetes. We need to understand this because you should have an idea of how things were and how it moved towards Kubernetes altogether or containers altogether, and how the production environment used to work and how they work now. And this will help you figure things out much easily, and you'll be able to differentiate things much better. So let's begin with this. So to understand how Kubernetes came into the picture, we need to go back in time and see about different eras and how deployment system changed, right? So there are basically you can characterize them into three parts. First is the traditional deployment era, then is the virtualized deployment era, and the final one is the container deployment era, which we are in right now. People are using a lot of different containers for doing stuff, and there are different ways of creating container, and Docker being one of the most prominent ones. I would recommend you to learn a little bit about Docker so you can understand Docker containers, because we'll be using Docker containers inside of our Kubernetes. Although throughout the module, as we progress through, you wouldn't have to use Docker commands as much as you think or anywhere in that entirety, but it's important to know what is the underlying architecture that you're working with, right? So that's why I recommend reading a bit about Docker. So moving ahead, so let's talk about the traditional environment, that traditional deployment era, and how we used to do things initially. So initially organizations basically ran on physical servers, as you must know that there was no virtualization or containers beforehand. So what they did was they had physical servers and they used to put applications on there, and the applications entirely ran on the physical servers. And there was no way to define the resource boundaries for any application in the physical server. So if you have, like, let's say any application which is on a physical server, it will, what is basically do is everything is available to it, right? So this application has access to everything, and the other application also has access to everything. If there is no, let's say, boundaries or restrictions on these resources, that there may come a time where some application requires some resources which are completely not available due to the allocation issues, which will basically lead to your application underperforming. So that was a huge problem when we were in the traditional era. So for example, if you have a multiple applications running on the physical system or physical server, there can be instances where one application would take up most of the resources, and as a result, other applications would underperform. As you can see here, this is the basic structure of how traditional deployments look like. So at the base level, you have your hardware, so basically the servers and stuff, and on those you had an operating system and you have different apps, right? So everything had access to the same resources, and that's why there was allocation problems here and there, and this was not a very efficient way to do things, but this is how we knew things would work at that point of time, so we went with that. This worked pretty well when it was there, but people soon realized that this is not very cost effective, it is inefficient, it causes a lot of error, a lot of different problems, right? So they decided that they'll move to the virtualized environment. So what they basically did in this methodology was you'd run the virtual machines, that is a VM, on a single physical server CPU, right? So, and the virtualization will allow the applications to be isolated between the VMs and provide a level of security as the information of one application cannot be freely accessed by the another application. So how you can think about it is, right, if you know about VMs, then you would be able to crack this more easily. Just think about you having one PC, right? On the top of that PC, what you did was you created two virtual machines, right? You have one OS, that is fine, but on top of that you have two virtual machines who think they have access to the OS completely, like they are the OS, they have the access to the entire operation, but there is a hypervisor which makes them feel that they have the access to everything, but they actually don't. But what this creates is both the virtual machines which we have right now, both think that they have access to all the resources, right? But So this basically gives you an isolation between the applications, like both of them think they are on two different environments, so you cannot exchange information. Whereas if you were able to hack into the physical servers in the traditional environment, there you can get information through of different applications at one place, and you can easily penetrate through if you have hacked one app, right? Here that is not the case, because there are two different OSs running on one virtual environment is running and another virtual environment is running. There's no correlation between those two, so you cannot actually access the information. And this basically helps you also isolate, remove the problem of the resource allocation, right? Because the hypervisor manages both of that, right?
Just a quick info, guys. Intellipaat does provide end-to-end training on Kubernetes. So if you're interested, you can check out the course details given in the description below. Now, let's get back into the session.
So as you can see in the virtualized deployment architecture diagram that we have here, so you basically, again, you have your one physical server, and on top of that you have one OS. On the top of that OS you create a hypervisor which can run two virtual machines, right? Two or many more depending on what the configuration is. And on top of that you have another OS of that virtual machine. So he thinks that this is the OS which is running, which might not be the case, right? And on top of that it's the same. Then there is the bin library and there is applications. So this is a much better way of doing things, because you're using only one physical server and you're basically deploying two sets of apps and work very easily, and you have more abstraction to the information that you have on both of your different OSs, and it's much more secure, much more effective, cost effective, as well as efficient. So this is much better than the traditional environment. So what I was talking about, again, this allows for a better utilization of resources in the physical server, and also allows better scalability because the applications can be added or updated easily. It reduces hardware costs, so that is the cost effectiveness of using the virtual environments, and there are much more. And each VM can be thought of as a full machine running all the components, including its own operating system on top of a virtualized hardware, right? So I mentioned this before. So because of the hypervisor, it thinks that they have access to the entire hardware, which is a virtualized hardware. So that removes the problem of resources and stuff like that. And it's very, very, very efficient and cost effective to do things like this. And then from there, we moved on to containerized environments. So it's kind of similar to VM, but much more cost effective again. So it's similar to VM. A container has its own file system, own CPU, memory space, process space, and everything, like much more. It has everything similar to that, but as they are decoupled from the underlying infrastructure, they are portable across clouds and OS distributors. So these can be moved across cloud and OS distributor. What it basically does is, and if you have a containerized environment, it only has, let's say, just the required things that you need to run that particular application. You don't have, when you design an OS, you prepare for a lot of different scenarios which it has to run through, right? It has to go through everything. So you create an OS for doing a lot of different things. So it comes out to be GBs and stuff like that, right? So when you create a container, you just need some particular things and libraries and stuff like that, which are absolutely required to run something, right? So that would come down and make your image to be like 80 MBs or something like that. It's very, very, very small. So 80 MB compared to a GB is like night and day. So it's a much more efficient if you are using containerized environments, and it can still run with the similar efficiency, and it becomes portable to use across clouds and OS distributors because it's just 80 MBs, right? So container have relaxed isolation properties to share the operating system among the applications, share the OS, and that's why considered lightweight. As I told you, it's like 80 MBs, right? So now let's quickly talk about the features of containers. So there's been a lot of talk about how good containers are when coming to the production environment, how lightweight they are, how portable they are, and how they have provided this abstraction level and max efficiency that we have seen so far. So let's see the different features of containers now. So containers are becoming popular because they have many benefits. So some of the containers benefit listed below. As you can see, you can talk about, here are 3 to 5, 3, so 6 to 8. Here 8 different advantages we have mentioned here. So agile application creation and deployment is one of those advantages. DevOps, dev and ops separation concern is another advantage of containers. Cloud and OS distribution portability is another very huge advantage. Then these containers are loosely coupled, distributed, elastic, as well as they allow for liberated microservices. Now this is a huge advantage again. Then there are application centric managements There is continuous development, integration, and deployment. The next advantage we can talk about is the environmental consistency that these containers provide. And finally, we'll talk about the resource isolation and utilization, right? So let's talk about these one by one. So the first one on our hands here is agile application creation and deployment. So what it basically does is it increases the efficiency and the ease of container image creation compared to VM image use. So basically pulling an image for 80 MBs is much more easier than deploying a complete virtual environment worth of a GB or more, depending on which OS you are going for. So it's much more easier to create these environments rather than your VMs. So basically that is what agile application creation and deployment, it provides that ease for that environment, for creating those environments quickly so that you can quickly get on with the work. So that gives us the ease and efficiency. The next one is dev and ops separation concern. So what we basically mean here is we basically use containers to create application containers images at build/release time rather than deployment time. So it essentially separates the application from the infrastructure. So let me explain this a little bit further. So basically there are two different domains before the era of DevOps. So what basically was, one was the development side of things and one was the operation side of things. So the development side of things is basically responsible for writing down and creating the application that you will be working on, and operations side was the one who was responsible for deploying it and maintaining it as it goes along, right? So the problem that they were facing was sometimes there will be different kinds of environments that they are working on which will be uncompatible. So when you go for the build and release time, there will be when you're going for the deployment, there will be a lot of different problems with the environment, or something or not will be compatible with each other. So that used to create a lot of problems for us. So what we decided was we can have the same images running from the start, that is the get-go, when you try to build an application. So that eliminates the possibility of having those errors towards the end. So that saves you a lot of time, because there used to be a lot of different problems when creating applications on two different sets of environments and then maintaining it. DevOps having containers gives you the platform of eliminating those problems, because you are working on the same image from the get-go, and therefore there will be very less compatibility issues because you don't have different kinds of OS running through your systems, right? You're working on the same environment, so it will be much more compatible and it will be easily integrated. Also, since you are working on a similar image and you're not let's say I have created an environment which I already have, and that infrastructure is up and running on my website or somewhere, or any application that you have, and now you want to attach something. So that infrastructure which you have running may have different compatibilities that goes along with it than the one that you have just created. So merging them sometimes can create a lot of problems, but since containers give you the advantage of working on a similar basis, so that basically allows you to merge faster and remove the errors towards the end and saves you a lot of time, right? Moving ahead, we have cloud and OS distribution and portability, right? So basically the same thing again, it runs on Ubuntu, RHEL, Core OS, on-premise applications, Google Kubernetes, Engine, and anywhere else. So you have all of these different cloud and OS distributions which is present, and you can basically move your whatever container images that you have from one OS to the other, or one cloud platform to the other. You can pull images directly. So that basically allows you to have a portable environment which can be used anywhere. So that is a very good advantage to have. Moving ahead, they are very loosely coupled. Distributed elastic service is also there, and there are liberated microservices. Now what it basically means is your application, let's say you have a 3-tier application, it can be broken down into smaller, independent and simpler pieces. Like if I say my 3-tier app can have 3 different layers, right, which can work individually, and all of these together finally give me the application that is required. So what we can do is we can deploy them on 3 different containers, so that it allows them to be independent on their own, and when you are working with it, it can be managed dynamically. So it allows you to have 3 different kinds of microservices running, which is much more efficient. And since it is distributed, you have this another layer of security also going for you. So that's very good to have. Moving ahead, there is application centric management. So what it basically means is you raise the level of abstraction running from an OS on virtual environment. virtual environment to running an application on OS using the logical resources. So as I was saying before, like in traditional environment, we have OS, which is running on the physical servers. So if you have many applications running, you can just basically get into one of those and maybe get access to the information of all the other applications. Now, since if when you move from there to a virtual OS, you end up having this basically two different virtual resources running, and it creates a level of abstraction. Abstraction is hiding the data basically. So you create this level of abstraction between the two VMs and you can hide your data more.
Just a quick info guys, Intellipaat does provide end-to-end training on Kubernetes. So if you're interested, you can check out the course details given in the description below. Now let's get back into the session.
And now let's think about going to containers. You have one application which can be further divided into smaller pieces, and you have many applications like that. So you can create a lot of different containers which are basically working on the logical resources rather than the actual resources which are physically present. So it makes it much more harder to reach them, hence creating this another level of abstraction as we go above and up. Like if we go breaking them smaller and so into smaller and smaller and smaller pieces, so it creates this next level of abstraction which is very much desired. The next one is continuous development, integration and deployment. So it basically provides for a very reliable and as well as frequent container image build and deployment with a very quick easy rollback. So again, it's the same thing as I was talking while explaining the DevOps thingy, that the DevOps basically works on containers because you have reliable and frequent container images that you can pull and create, and it is very easy to do that. And while merging these two containers, there will not be compatibility issues because you are basically pulling the same image, so it will be almost the same configuration is almost there, so there's no compatibility issues also there, so it saves you a lot of time. And let's say if I create something which has some problems here and there, so there is an option to easily roll it back to the previous version. So that gives you this advantage of not having downtime on your systems. As soon as you know it is not working out, just roll your systems back to the previous container images and it will work perfectly. Right? Then we have two more advantages on our hands, which is environmental consistency and resource isolation and utilization. So environmental consistency is again is the same thing. It runs the same on as it will run on a cloud, so as it will run on a laptop. So if my image is running on that laptop, it is the same as if I pull an EC2 instance from the cloud and if try to work there or something like that, it runs the same because it's pulling the same image. So that gives you this environmental consistency, which will allow you to work more efficiently. And finally, we have resource isolation and utilization. So you have predictable application performance and high efficiency and density of the things that you can do. So you have logical set of resources which can be used much more efficiently because the applications are going at it at all times. So you have better management of resources altogether, and you give more density, that is work done per unit time if you can take. So that provides you with a higher efficiency and higher performance rate. So that's a very good advantage to have again. So let's talk about Kubernetes now. So basically containers are a very good way to bundle and run your applications. We talked about this before, right? You can have your applications divided into a various number of small independent pieces and you can bundle them together and run it dynamically and manage it. So right. So in a production environment, you need to manage these containers, right? So there are a lot of containers that you have broken your application down into. So you need to manage these containers to ensure that there is no downtime and there is no hindrance here and there. So that is where Kubernetes comes into the picture, right? So what basically Kubernetes does is it provides you with a framework to run on your distributed systems very resiliently. So it takes care of all the scaling that you have to do. So by scaling, I mean if you have, let's say, 3 replicas of a pod, we'll discuss about pods later. So you can make it 4, 5, 6, 7 or bring it down depending on your needs. And if there is a failover for your application, it can rebuild it if it's required. If it gives you with a deployment pattern. So there are 2 ways of basically deploying things. You can recreate it. So what it means is basically if you have, let's say, 2 things which are running and you have an update right now, so you can either recreate the entire thing, which will give you a little downtime, or you can go with the rolling updates. So the rolling updates will basically move it one by one, all the replications that you have, and replace it with your new updated deployments, right? And it provides you with much more than that. So basically Kubernetes can be thought of as a portable, extensible, open source platform which is used for managing containerized workloads and services, and it facilitates both declarative configuration as well as automation. So it does both of those things. So what do we mean by declarative configuration? So you give your configurations as a file where you declare, okay, this is mapped to this, so this basically does that. So we'll talk about that when we talk about YAML files, and it gives you this automation kind of thing where it basically manages all your things through controllers. So it has a very large and rapidly growing ecosystem, Kubernetes. So various number of people are involved with Kubernetes ecosystem. A lot of people are there, so they give you this service and support, and there are different tools widely available which are very compatible with Kubernetes. So a lot of people are working with it. So there is a huge community to it where you can find different answers to the problems that you face in and around different communities. So it's a very, very, very happening and hot topic in the computer science field right now, and specifically towards the DevOps. So Kubernetes is a very, very good container orchestration tool. So it helps you manage all your containers and deployments and scale it, right? Let's talk about the different features that Kubernetes provides, right? So we were talking about how it is very much useful for managing the different number of containers that you have. It is a basic tool which allows you to orchestrate all your containers. And orchestrator can be thought of as something like if you imagine an orchestra. So there's this a guy who is going left and right with his hand and has a stick, and he makes everything work properly and make sure everyone works according to what he's saying. So not saying per se, but whatever he's signaling. So it maintains that harmony, that sync in that music. Similarly, for your applications to work, so there are a lot of different containers who are doing different things. Kubernetes is the one who is doing the orchestration here, so you can manage them from one resource, right? So Kubernetes is one of the most popular technologies out there, and it is down to the numerous features that it has given or supplies, which separates it from the rest of the competition which is out there. So basic advantages have been mentioned here as service discovery and load balancing. There is storage orchestration, there are automated rollouts and rollbacks, then there is automated bin packing, self-healing, and secret and configuration management. So these are the few advantages that it provides, which separates it from the rest of the tools that are out there. So let's look at these advantages one by one. So the first one is service discovery and load balancing. So Kubernetes can basically expose a container using DNS name or using their own IP address. So if a traffic to a container is high, Kubernetes is able to balance the load and distribute the network traffic so that the deployment is stable. So let's imagine you have 3 replicas of this one website that you have. Let's say the people are pinging the website again and again, and it becomes huge traffic is there because you gave some 50% off or something on your product. So there's a lot of people entering. So now your one container has a lot of traffic, which it is not able to deal with. In that scenario, what Kubernetes will do is it will manage the traffic across, if let's say we have 3 replicas of the same file. So it will manage the traffic across 3 replicas so that none of them is overburdened, and it will make sure that your deployments remain stable, right? Next one is storage orchestration. So Kubernetes basically allows you to automatically mount a storage system of your choice, such as local storages, public cloud storages, and many more. So when we talk about volumes in the coming sections, which is I think it's in module 4, there we'll talk about the various kinds of storages that you can use. You can use persistent volumes, you can use MTDIR, there is AWS storages, there is Google Cloud Storage. There's a lot of different things that you can use, and Kubernetes is compatible with all of those, so it allows you to automatically mount these storages and work with it. So it's a very good advantage to have that flexibility across the different kinds of storages, right? And then there is automated rollouts and rollbacks. So basically what you do is you describe the state of your pods or your containers or your deployments in this configuration file. So we were talking about how you can write configuration files, that is the YAML files. So you define in there, so this is what I want my containers or my pods to be in this state, right? So let's say I always want my application to have 3 replicas. So there will be 3 different copies running at all times. And if something were to happen, let's say something happened and one of your pods crashed or failed. So it actually got killed. It is unresponsive. So it was killed. So now you have 2 replicas only, right? So it's the job of the Kubernetes to make sure that if you have described that you need 3 replicas, it will recreate a replica for you. So that is where a bit of automation also comes in. So it allows you to automatically roll out and roll back. And also if you are rolling up, you are providing a rolling update, and let's say you updated an application and you have like 3 replicas, and in the middle of it you realize, oh no, there's a bug in my file, so I need to go back to the previous version. You can do that as well. It will take all of the replicas down one by one and change it to the previous image that it was running, right? So it controls basically your cluster to be in the desired state as you defined it to be, right? So the next one is automatic bin packing. So you provide Kubernetes with a cluster of nodes that it can use to run containerized tasks, right? So you tell Kubernetes how much CPU and memory, that is RAM, each container needs, and Kubernetes can fit your containers onto the nodes that make the best use of your resources.
Just a quick info guys, Intellipaat does provide end-to-end training on Kubernetes. So if you're interested, you can check out the course details given in the description below. Now let's get back into the session.
So you can describe your pods also as well as your nodes. So sometimes you have some nodes which have dedicated memory or dedicated hardware such as GPU. So there are some applications which require GPU. So in that scenario, what you can do is you can allocate where which container should go in order to make the most efficient use of your resources, right? The next one is self-healing. So Kubernetes restarts the containers that fail, replaces the containers, kills the containers that do not respond to your user-defined health checks, and it doesn't advertise them to the clients until they are ready to serve. So as I was telling, like let's say I have 3 replicas and one of them becomes unresponsive. So it's the job of Kubernetes that it will kill it, then it will recreate the container. While it is unresponsive, it will not show that container to any clients which are trying to ping that pod. So it will not allow it to go there because it knows it's unresponsive. So it will point it to some other replica, but not that one. And then it will kill it. It will create a new replica. And when that new replica is ready to serve, only then that will be advertised to your clients. So it basically shows that Kubernetes is very self-healing and works perfectly in that scenario. Then there is secret and configuration management. So Kubernetes allows you to store your sensitive data such as usernames or passwords. There are authorization tokens, SSH keys. There's a lot of different things. You can store these sensitive information in the form of this volume called secrets and the application configuration without rebuilding your entire container images, right? And without exposing your secrets to your stack configuration. So you can basically work with secrets to encrypt your data and work properly with it without having to run the risk of exposing it to your other stacks. Let's take an overview of how actually Kubernetes works. So we'll try to imagine how things actually work when working with Kubernetes, and I'll try to explain the different concepts that goes along into working of it, but you'll understand the better infrastructure altogether when we talk about the architecture of Kubernetes in the next module, and you see all of these things that I mentioned here in the coming up modules so that you can tie them all up together and understand the concepts really well. So please bear with me for the next whatever the minutes are. I'm trying to explain the working of Kubernetes. Just take it as a concept, as an overview, and as we move along the modules, I can bet it'll get much clearer. So let's talk about this concept here. So the first before we begin with the explanation and the next step from here is installation for us. So before we get into that, let's discuss a few concepts in Kubernetes, and these concepts which I mentioned some of the names here. For example, I'll be taking the name of services, I'll be taking the name of pods, and I'll be taking the names of something like an ingress. These we'll be discussing later on, so that is not something to be worried about, to be honest, and we'll take care of that as we go further, right? So let's take an overview of how things actually work. So let's begin with pods for the first hand. So basically pods generally refer to one or more containers that should be controlled as a single application. A pod encapsulates application containers, storage, resources, and a unique network ID and other configurations on how to run containers. So let's imagine your application can be decoupled into 3 small containers, and these small containers together can be called as a pod. Now these pods can have many replicas as well. So let's say I want to have 3 replicas of this one application which has 3 different containers inside of it. So I can create that, and we can get different pods along with it, right? So that is that, and you just think of pods as a set of containers. So you have a set of containers inside of pods, right? And what people generally like to do is have multiple replicas of pods, because Kubernetes will track the pod health and remove or add pods as needed to bring your application to the desired state. So you write these YAML files where you can actually describe the configuration and the desired state of your particular application. And if it does not match, let's say if you have 3 replicas and it does not have 3 replicas at the moment, it will add or remove the number of pods based on the number of pods that you actually need to match your desired state. So that is what it means here. We've been talking about replicas a lot when we began this module as well. So now imagine that you have created an application. Let's say it compresses images. Now it's fully functional, and you used a deployment. Deployment is another concept that we'll be discussing later on. So you basically use a deployment and you created 3 pods, right? And now the customer doesn't know which pod to go. So you have 3 different replicas, right, of the same thing. Now you don't know where to go and what to do, which IP to hit. So what you do in that case is you basically create a service, right? So the job of a service is to represent a logical set of pods. So what it does is acts as a gateway, allowing the client to send requests to these services without needing to keep the physical track of these pods that you have. And these services are basically a logical set of pods. So what it does is basically hits the service IP or service name, whatever that it knows, and this service will basically map you to the required pod that you need to work with, or the pod which is not busy, or pod which is up and running and serviceable, right? So you do not actually need, as a customer, to know what is the actual location of the pod with the IP address. You just need to hit the service. And then again, inside of services also, there are 4 different kinds of services that you work with. So not all the services are externally reachable, right? There is only one kind of service, which is node pod, which is externally reachable. And so a lot of times you don't really want to use a service of that kind. And for that, people, what they do is they create another concept on top of this. So first layer is pod. Above the pods is services, which is a logical set of pods. Sometimes these services are not exposed to the external environment, so it can be of the type cluster IP, which is not exposed to the external nodes. So in that case, you create this concept called ingress. So what ingress basically does is it can be used to create externally reachable URLs, which will load balance the traffic, terminate SSL as well as TLS, and then offer name-based virtual routing. Now what I mean by name-based virtual hosting is the fact that sometimes you go to let's say www.intellipaat.com/. So whatever I put next is a kind of can be thought of as a name-based virtual routing, that I'm just putting the name. Based on that name, it hits an IP address. So that IP address, now that redirects it to a service. So that ingress is routing, that ingress IP is at that location, that is routing you to the port where the service is exposed, or you can, if it's a cluster IP, it can redirect you to that service. It will go to that service. From that service, it will show a logical set of pods. So whichever the pod is available at the moment, it will go to that pod and retrieve the relevant information. It will hit the service, and service will talk to ingress again, and that's how the entire system will work, right? So you basically have pods. Since you don't know which pod to hit, you have a logical set of pods, which is called service, on top of these pods, which can redirect you to the actual pod which is working and required for you. And since these services are also not externally reachable in many cases, if it's cluster IP or the other kinds, so you create this thing called ingress, which allows it to create externally reachable URLs that the customers can hit, and it will allow a name-based virtual hosting as well, and you can load balance the traffic, and you can run multiple hosts on the single IP as well using these ingress, right? So this is basically how Kubernetes works overall. If you didn't understand, just don't worry about it. As we go through these concepts one by one, you'll be able to understand it much better. We'll get into the details of each of these concepts, that is pods, deployments, as well as service and ingress. And this is how the Kubernetes works from the outside. That is how it looks at it, works from the outside. These are the concepts which it looks like it's working from the outside. We'll discuss the architecture inside of Kubernetes and how things are working internally in the next module when we talk about the architecture of Kubernetes as well. So there's a lot of learning involved working ahead. So just keep these concepts in mind. You have heard this name, this is on top of this is on top of that, and that is how it is running. Just keep that concepts in mind. So when these concepts come later on, you'll be able to just quickly connect the dots. So I'm just laying the dots out here right now, and then as we move along the modules, you'll be able to connect the dots and make the complete sense out of it, right? So that's that. Now let's quickly install Kubernetes on our EC2 instance. So what I'm following is a kubeadm installation, and I'll be installing that on my EC2 instance. So this green one right here is my master, and this is my slave. So I'll be creating a cluster and I'll be joining them as well. And for doing this installation, there is a lot of different commands that you need to run in here, right? So you can either go to their official documentation, that is kubernetes.io.docs, and then go there to actually get the installation steps, or you can just follow, if you are following some other kind of installation, you can do that, or you can just follow this documentation that we have prepared for you. So I have mentioned all the commands that you'll need to run in order to get Kubernetes installed on both of your systems here. So let's begin with the installation. So what I'll be doing here is quickly copying some commands from my documentation, and I'll be explaining some of those commands, and we'll see the working of installation of Kubernetes, right? So let's begin. So the first command is sudo su. So we'll just quickly type here both places sudo su, just to show you that both the instances are working. Post this, I'll be just copy pasting everything. So that, and this next command is apt get update, right? So this is something which you have to run all the time when you're working with Ubuntu. You're installing anything, you need to get the apt update, right? So let's get the update. So as you can see, it's running on both the systems. So it's done in the master, slave it's running. So the next command we have here is apt get install docker.io #install docker, right? So this command basically installs Docker to your machine. So we'll run that on both master as well as slave, and you'll be asked if you want to continue, just press Y here, and you have to do the same for the slave. So we'll run that on the slave as well, just to show you. We'll press Y here as well, and we'll wait for it to actually install Docker on both the places. As it goes through that, let's look at our next command. It's been done in our master. The next command is apt get update and install apt transport.curl. So this is the next command that you have to run. So after this command, you should see a very simple downloading of few packages. Run it in both master and slave again. After this command, we are curling a package. So after this command, you'll basically get an thing saying that it's okay or something if it's properly working. So post this, you should see an okay, right, like this. Similarly in the slave, you have to do the same here. So we have ran that command. The next command is cat eof Kubernetes list, and we have to pass few arguments in it as well. So we'll copy this commands again in master, and so it's not completely copied. So as you can see, li was there, so it has to be copied till list, right? So this is here, just run it here, and same for the slave, and the next one, which gives the area where the actual Kubernetes main deb is there. So just pass that, and this one as well. Then type, since we've opened an EOF, we have to type EOF to get out of it. Just press EOF in both places, right? So EOF is done. The next command is again apt get update. So after we have done that, we just need to get update once more. Run it on both your master as well as your slave, this command. When this is done, the next step we have to do is we have to install kubelet, right? Kubelet and kubeadm for kubectl, right? Install those things. So that command is next. So we are installing here those, and run it on both of your machines again. The next command here is to be the step 5, which is initializing the kubeadm. You need to run this command only on master. Now let me explain this command as well. So we are initializing our kubeadm. So we need an master private address for it to run. So here in this place, you need to add your private address of your master, and the pod network we have given as this one. And this command that we have mentioned here is ignore pre-flight errors as well as is equal to num CPU. So actually sometimes what happens is you need multiple CPUs in order to run these commands, because 2 is the requirement. Sometimes you only have one on your instance. So if that is the case, it ignores that. I've mentioned it here for you. If you are running an instance with one CPU, it will ignore those errors and continue with the installation, right? Let's see if it's been done here. So this command is only to be run in the master. So just copy here. As you can see here, I have to mention my master private address. So I'll just quickly wipe it off. Right, and then go to my EC2 instance and look at the private address of my master, which is this 172.31.33.241. I'll just quickly copy it again. Go back here, paste it in place of where the address should be, and once we have done that, let's read the command. Looks fine to me. Just press enter and hit run. Once you have done this, you have to wait for a couple of seconds, because it will give you a joining token. That token you have to pass it through to your slave, and that's how they connect. through that token. It authorizes it to connect through, which creates a basic, let's say, a gateway kind of thing between the two, where they both can interact with each other. That is a message of confirmation, if you will. It's a security practice which is very well followed everywhere, because you need authorization tokens in order to do things. So we are waiting for the kubelet to boot up and control plane as the static pods from the directory are doing something. And you can see here towards the end, then you can join any number of worker nodes by running on each root as this. So the command, if you have run everywhere, if you have, let's say, n number of nodes which you want to attach to this master, you just need to pass this command through them and you'll be done. So I've copied this here. I'll go to my slave. I'll run this command. As you can see, it's doing. So it says run kubectl get nodes in order to find out. But before we do that, we need to make a few changes to our master in order to run as the user. So currently, right now, we are in sudo su, which is the root IP directory. So we need to get out of it. So I'll just press Ctrl D to exit that, and then just paste our command, making a directory in the home, and I'll make some changes there. So I want to basically create a kube config, and in that configuration, I have to give some permissions. For that, I'm using sudo chon, CHOWN. I don't know how you pronounce it. So to make those changes, and as you can see, the ID I'm passing here as, and I'm passing another one here. This is username and configuration, admin configuration that we need to pass. So that is that there. So we'll just quickly paste that as well. And once you have done that, if you do kubectl get nodes, what will happen is it will show you the nodes which are not ready, because we have not created a network yet, right? So if it shows you two nodes which are not ready, don't panic. You are on the right path. You have created a master 113 seconds ago and a slave we attached to it 81 seconds ago, right? So the next we need to do is we need to create a network, right? And that network plugin comes through this. You need to run this command. It keeps on updating. So if by the time you are reading this material and they have gone through an update that we have not noticed, just quickly go to their documentation files and look for Calico network plugin that they use for Kubernetes, and it will work. You just need to run it in your master. Just quickly run this one. And if I do kubectl get nodes now, I have a master which is still not ready. Just wait. As you can see, now it's ready. Not ready was here. Now it's ready. Now if I do kubectl get pods -all -namespaces. So it will give me all the pods in the different namespaces. So these are the different pods that Kubernetes is running currently to make the installation happen and make the Kubernetes system run entirely. So now we are done with the installation. The Kubernetes is running perfectly, and that's about it. So you can follow these instructions, or if you are installing in some other environment, you can follow the installation guide if on the Kubernetes website, official documentation.
So let us begin with Kubernetes architecture. So basically Kubernetes follows a client server architecture. So basically there's a client, there's a server, you send a request to the server and it replies back, something like that. So along the ways, it follows a similar architecture to that. In this Kubernetes architecture, we have a master installed on one of the systems, and there are a lot of different slaves, as you can call them, or different nodes which are on the separate systems, and these are connected. So there's one master which controls everything, and there are a lot of slaves to it, or different nodes to it, which are created on different separate Linux machines. So as you can, if you remember in our installation, when we tried using the AWS console, so what we did was we had multiple instances, out of which one we had as a master, and rest of them we attached them with the token as a slave. So that's how the architecture is, and you can see the overall architecture here in this picture. So there is this one master node right here. Now master has different components to it. If you look at it, this is a worker node, this is another worker node, and here you can see a master node has an API server, a kubectl. A kubectl is basically a command line interface, which we'll be discussing on later. And there's an API server. So as a master, it has to host, so it has an API server there. And then there is a scheduler which can schedule different jobs, and there is a controller manager. So there are a lot of different things which can be controlled, which have a controller manager, which makes sure that certain things are created and maintained, if you will, for their requirement. And there is etcd, which is another part of the master component. And then in the worker node side, you can see there's a kubelet, there's a kube proxy. There are different pods, and then there is on above it, it's a Docker, but you can have any other containerization platform. If you have, you can create containers through that. You can use that as well. And then there is the internet. So we'll be hitting each of these individually one by one. So if you are starting off, so let's start off with the master. So we saw there was etcd, there was an API server, there's a kube controller manager, there's a scheduler, and there's a cloud controller manager. So we'll hit all of these one by one now. So basically etcd is something that stores configuration information which can be used by each of the nodes in the cluster. It is a highly available key value store which can be distributed among multiple nodes. Also etcd, the job of it has to store all the configuration and the specifications, and it has to be readily available across all of the nodes, so that there's a constant availability of things and you know what is going on, right? So these configurations are accessible only by Kubernetes API server, as it may have some kind of a sensitive information. So it is kind of an encrypted area where you want to keep your sensitive information as a key value store, and it is a distributed key value store which is accessible to all. So this key value store contains all of the configuration information and other sensitive information that is required for it to run. So it this information helps Kubernetes node and server architecture stay alive, and it is just sometimes called as the brains of the Kubernetes, as it has all of the information which is required for it to run. And the next part is the API server. So as we mentioned, the API server is the one which is the only one that can access the etcd, right? So this provides all the operations on the clusters using the APIs. So there are different APIs. As we mentioned, it is a client server platform. So there's a lot of information which is all of the work which is done through APIs. So this makes sure that all the operations which are done on the clusters are done using the APIs. API server implements an interface, which means different tools, libraries can readily communicate with it. So it is a very key part of the architecture. And then there is a kubeconfig package along with the server side tools that can be used for communication. So what it basically does, that kubeconfig thing, is basically exposes the Kubernetes API. By exposing, I mean there are some things which stay internal and some things that you expose which is publicly available that you can see from the outside. So the kubeconfig package lets you expose your API so that others can reach it from the outside, right? So Kube API server is designed to scale horizontally. That is, you can scale more and more by deploying more and more instances. So if you want to scale the architecture, so in order to do that, you have to create multiple instances and divide your workload along it, and it scales horizontally. So it scales horizontally in that way. You can run multiple instances of a Kube API server and balance the traffic between those instances. So if you have multiple nodes, easily you can transfer whatever the traffic that is coming on, or whatever the request that the client is asking for, you can serve those by balancing those traffic throughout the nodes that you have with the help of the API server, as you have multiple instances. Coming to the kube control manager, it is the component on the master that runs the controller. Logically, each controller can be thought of as a separate process, but to reduce complexity, it is compiled into one binary and run as a single process. There are various components of the controller. So these are namely basically four kinds. First is the node controller, which is responsible for noticing and responding when the node goes down. So you have a lot of nodes. If you are creating like multiple nodes, so it has to make sure that all of the nodes are running. So our node controller's job is to make sure that it notices and responds when a node goes down. Then there is a replication controller. Now, when we'll be discussing YAML files, you'll see that you can have multiple replicas of a single pods, and you can have lot of like a pod can be thought of a set of containers, and those containers will have a lot of information, right? So if that container has your application, so you don't want one instance of that application to be running. You want it to have multiple instances. So let's say if I have a client which wants some service to be done, and that service is, let's say, image processing, and it converts image to black and white. It would be okay if I had only one customer. So now I have like 10,000s of customers, all of them requesting that their picture should be turned into black and white. But if you have only one instance, there will be a lot of traffic on it. So what you want to do is you want to have multiple replicas of the same pod. That is the pod which has the containers which basically turn the image to black and white. So what you want is multiple instances of that, so that each of them requests which are from your 10,000 clients can be served properly in a faster manner without having a downtime, and so that the traffic is also distributed. So the job of the replication controller is to make sure that if you define in your YAML file that I want, let's say, 10 replicas of this pod to be there, so it makes sure that there are always 10 replicas available, and if some replicas goes down or if it stops responding, its job is to recreate it. Okay, Then moving on, there are endpoint controllers, which populates the endpoint objects. That is, it joins the services and the pods, and it's basically making sure that the different endpoints of your application is running and they are in constant connection with each other. Then there is a service account and token controller, which create default accounts and API access tokens for different new namespaces that you have. You'll understand namespaces in this module itself. We'll be discussing that in the add-on section. Now moving forward, we have a scheduler. Now scheduler is again a very key component of master. It is responsible for distributing the workload. So if you have a lot of workload, its job is to schedule it and distribute the workload. It is also responsible for tracking utilization of the workload on cluster nodes, then placing the workloads on which resources are available, and then accept the workload. So it'll look at the resources that are available and then it will accept the workload, and then it's responsible for distributing it and tracking the utilization of whatever the resources that we have, right? So basically, in other words, what you can tell is that this is a mechanism which is responsible for allocating all the pods that are available to the nodes. So as I told you, there are a lot of different containers. So if you understand Docker, you know there are a lot. The basic container has a simple image. Now multiple of these containers together forms a pod, and this pod can be some kind of an application. So as I mentioned before, if we have multiple replicas of these pods, so there are a lot of replicas which can be deployed on a single node. And if one of the replicas is, let's say, busy or is down for some reason that it's facing some responsibilities, the scheduler is responsible for allocating these pods to different nodes and then making sure that if something is not working, then the work will be given to some other node. And that is the important part of the scheduler. Then moving on, then there is a cloud controller manager. Now cloud controller manager runs the controller that interact with the underlying cloud providers. So in our case, it was AWS. It could be GCE, which is the Google Cloud Engine. And there could be a lot of different, you can use Azure or whatever the cloud that you are using it. So cloud controller allows the vendors code. So that is the cloud vendors, whatever is your cloud vendor, if it's Microsoft or Amazon, it allows that their code and Kubernetes code to evolve independently of each other. So it can, both of the codes are working, they're working simultaneously on the same thing probably. So it makes sure there is a coherence among these two while they are working as a single unit. So it is a very important part again. So the following controllers, cloud providers have their dependencies. So there is a node controller, there's a route controller, and there is a service controller and a volume controller. So there are 4 kinds in this also again. So the job of the node controller is for checking the cloud provider to determine if the node has been deleted in the cloud after it stops responding. So if it stops responding, its job is to make sure that the node, to determine if the node is deleted or not. And then there is a route controller. So the route controller basically is for setting up different routes in the underlying cloud infrastructure. So it's basically responsible for where the information goes from where to where and routing it basically. So basically what a router does. Then there is a service controller, which is used for creating, updating, deleting cloud provider load balancers. So like we have a scheduler for distributing loads in the master side of things, in the, let's say, pod side of things or whatever we have. In the cloud side of things, the service controller is responsible for load balancing their traffic. And then there is a volume controller, which is for creating, attaching, mounting volumes. Now volumes are again can be thought of as storage, and it's a very this volume controller is responsible for interacting with the cloud providers to orchestrate these volumes. So as I told you, volumes can be thought of storage, like storage. So storage is there. So there's a lot of different storage. What you want is that your storage interacts or properly mounts and attaches itself to the cloud. So the job of the volume controller is for creating or attaching or interacting with the cloud providers and properly orchestrate, that is sending and properly giving the instructions basically, if you will, to these volumes to properly work with the cloud. Then coming to the node side of things. So the node architecture, as we saw earlier from the overall picture, contains of basically 3 major things. First is the container runtime, where we talk about different tools which are responsible for running your containers. Second one is the kubelet service, which is responsible for talking to etcd and the master and getting the information, which we'll discuss when we talk about kubelet service.
And the final one is the Kubernetes proxy service, whose job is to make sure that some things are available to the external host without any hassle. So all of these things have been designed in such a way that it becomes a very hassle-free job when you're working with Kubernetes. So let's hit them one by one. So the first one on our hand is container runtime. So a container runtime is a software responsible for running the containers. And as I've mentioned earlier, that Kubernetes is a container orchestration tool. It is not something that creates the container. It is something that manages them. So you need to have a software that creates the containers. So that could be Docker, and I've mentioned here that Kubernetes supports several runtime containers, which is Docker container, and there is Containerized, there is Creo, then there is Archlet. There's a lot of different things, or any other implementation of Kubernetes CRI, which is Container Runtime Interface. So you can use any of these to create your containers. So the first thing that is required in the architecture is a container runtime, something which creates and runs the containers. Moving on, the second part is the kubelet service. Now, this is a very small service in each node, which is responsible for relaying information to and from the control plane service. Now it interacts with etcd. So if you remember when we were talking about in master, that etcd is a distributed, highly available key value store which contains a lot of configuration information and specifications for your different deployments. So the job of this kubelet service is to interact with the etcd store and to read and store the configuration details. So it interacts with the etcd and it stores and reads and these configuration information, which is very responsible for us. It does more than that. What it also does is it communicates with the master component to receive the command and the work which is required for you to do. So the master and the node interact through this kubelet service where it basically communicates with the master component. Then this process also takes the responsibility for maintaining the state of the work and the node server. So it does three very major things. It does interact with the etcd to get the configuration information. Then it interacts with the master to know what is the command and what is the job to be done. Then it also makes sure that whatever the specifications that we have read and what is the state of the work is required, it is there and the node is maintained. Finally, it also makes sure a few of the networking side of things where it makes sure that ports are forwarded and the networking rules are well working and everything that is required. So it does all of that. So kubelet service is responsible for all the major networking related things. Then there is Kubernetes proxy service. Now this proxy service runs on each node and helps making the service available to an external host. So what does this mean? Let's give you an example. Let's suppose I told you before, right, that the pods are a set of containers which is deploying an application. Let's say I have two pods in one node, right? And both of the pods are mentioned as a replica of each other. Just what I've done is I've made a very small change in both of these pods, right? So since I'm an external person, I don't know where the pods are. I know where the node is. Maybe I know the IP of the node and I'm trying to reach that node, right? So what would be the information that I get? Will it be what it is inside pod 1, or will it be inside what is pod 2 or the container 2, whatever it is, or it is container 1 or is it in container 2? Which one do I reach, right? In that case, what will happen is when you don't know where it is, the job of the proxy service is to bridge that gap. Since you don't know where it is, it makes it look like you know where it is by routing you to the proper place. So if I hit the IP of a node, I do not know where actually the pod is, but the proxy service basically maintains that gap. It talks to the node and it communicates it to the pods and or the containers and gets back the information so that it looks like you are actually hitting the pods without actually hitting it. So it basically makes sure that that service, which is the whatever is inside your container, is available to the external host without actually them knowing where it is. It helps in forwarding the request to the correct containers and is capable of performing primitive load balancing. So as I was giving an example, so if I have two containers, if I make a very small change in both of them, let's say one says hello world and one says bye world or something like that. So the primitive load balancing that it does is if you hit that node again and again and again, there will be instances where you get hello world as the reply, and there will be some other instances where you get bye world as the reply. So that is the job of the proxy service, to make sure that you actually get information from the container without actually knowing where the container is. Its job is to bridge that gap. Moving on, it makes sure that the networking environment is
predictable and accessible at the same time. It is isolated as well, so it makes sure that it is predictable. So if I'm hitting a node, so I think it what I should receive what I'm expecting. It makes sure that it becomes predictable, that I get what I want, and it makes sure that it's accessible while I still don't know where it actually is. That is the time it's being isolated. So I don't know where it actually is, but I still receive the information with the help of this Kubernetes proxy service. That is the main job of it. It manages pods on nodes, volumes. Volumes are nothing but storage kind of things. Then there is secrets, which we'll be discussing on later on. So secret is something basically which you use to store information with an encryption. So if you have sensitive information like password and stuff like that, you can use secrets to pass that passwords on, or creating containers, health checkup, or whatever you want. Kubernetes proxy service does it for you. Now we'll be talking about the add-ons which are there in Kubernetes. So add-ons use resources like daemon sets, deployments, etc. to implement cluster features. These are all different features of a cluster that you can use because these are providing cluster level features. Namespace resources for add-ons belong within the Kubernetes namespace system. So if you have installed Kubernetes, right? You can just write Kubernetes get all pod -- all namespaces. You'll see different namespaces which are already available. Let me show you just before we begin. So this is my master. As we've been talking here in this slide, that there are a lot of different things which are there, and it will be available along with the kube system namespaces, right? So I'll just want to show you that if you type a very simple command, kubectl. Now kubectl, as we talked, is a command line interface that allows you to interact with your Kubernetes cluster, right? So this is there on the master. This is my master component. So kubectl get pods. I want to get pods, but what I want is since I've not deployed any pods, so if I do that, I'll get no resources right now. So because there is no default namespaces which is there. So what we want to do is we want to get all the namespaces. So we'll type kubectl get pods -- all - namespaces. We'll discuss about namespaces later on. So what you basically want to know is, like, if there is we define resources in different namespaces where they work. So if you type kubectl get pods -- all namespaces, we will see currently all of the different pods that are running inside of Kubernetes, which are responsible for its running, right? So as soon as I've hit, as you can see, these are all kube system. The namespace here of everything is kube system. Now this has Calico kube controllers. Now Calico is our basically our network manager kind of thing. This we installed, you have seen while we were installing it. There is an etcd IP, as you can see. There is Kube API server, then there is Calico Kube servers, there is Kube proxy servers, Kube scheduler, and everything. All of these information that we were discussing, core DNS and everything, you can see inside this is running, right? So let's get back to what we were talking about. So these are the different namespace resources. The add-ons belong within the kube system. So whatever the namespaces that add-ons that you will be adding, these all belong to the kube system namespace. As we saw, when we did all namespaces, we saw kube system, whatever namespaces it had. We did not add many add-ons in there, but there are a lot of different things still. So there is DNS. The DNS is a mandatory add-on. So in my, if you can see my terminal again, this kube DNS was already present in here. This core DNS, this is still inside the kube system. The core DNS is already present. So DNS is a important mandatory add-on which is there, but along with that, there are a few other add-ons that you can use. There is a web UI dashboard. There is a container resource monitoring tool which you can use for monitoring how the status of your containers are right now. Then there is cluster level logging also. We'll talk about that, all of these in detail in the future modules, but we'll give you a zest of it now, because we'll show you even how to set up your web UI dashboard for Kubernetes. We'll even show you how to monitor these resources, which we'll be using for using Prometheus and Grafana, where Grafana is used for visualizing those information. There is cluster level logging. We'll show you all the logs and stuff as well in the hands-on in the future modules. But just now, we just need to give you a zest of things, so we'll explain it to you here. So starting off with the DNS. Now, cluster DNS is a DNS server in addition to other DNS servers in your environment, with server DNS records for Kubernetes service. Containers started by Kubernetes automatically include this DNS in their servers. DNS server in their DNS searches. So I was telling you, this is a mandatory add-on. This you need to have if you want to work with Kubernetes. It's already present, predefined in it already. But the other things which we are going to talk about in these add-ons, they are not very necessary when you're working with it. It's a good thing to have them as well because it helps you work better, faster, and in a more informative way. But this is something which you actually require. Moving on to the web UI dashboard. Now, dashboard is a general purpose web-based UI for Kubernetes clusters. It allows you to manage, troubleshoot applications running in the cluster as well as the cluster itself. Even you can when you go with the web UI dashboard, which we'll show you after on. So all the concepts that I'll be teaching you how to run through a command line interface, you can do most of it through the dashboard as well, but we'll be teaching you command line interface because it is important for you to learn how to use command line interface when you're running with the Kubernetes, because it gives you a better zest of things, and not all the production environments that you'll be working with will allow you to do dashboard based things, right? Moving ahead, there's a container monitoring resource. So container resource monitoring are generic time series metrics about containers in a central database, and it provides UI for browsing that data, right? So for this, you can use a lot of different tools again, but what we'll be showing you in this course is using Grafana as well as Prometheus and Helm, where Helm charts are used to get data through Prometheus, and we visualize those data through Grafana. So we'll be showing you that as we go along the modules. But basically, this is used to see how your nodes are performing, how their health are, and how many of them are getting killed and they're restarting and stuff like that. All of that data you can get and monitor your containers, right? Then there is a cluster level logging. Now, cluster level logging mechanism is responsible for saving the container logs to a central log store with search/browsing interface. So all of the containers that you have, they have logs of their own, right? So what you can do is sometimes when you want to receive some information or when you're trying to troubleshoot or debug something, you need to have the information of what your container has been through. So cluster level logging mechanism is responsible for that. It stores all of the container logs to a central log store with search browsing interface. Now next is kubectl. Now kubectl I'd say is not just add-on, it is again a very mandatory add-on. It is a part of the master, if you will. It allows you to basically communicate or interact with the Kube API server and send commands to the master node. Each command is converted to an API call. As you saw in the example that I showed you, I had a command line interface that was my bash terminal, and there I typed kubectl get pods. Now that is a command. Now that command is turned into an API call, which is through the API server. It is sent to the nodes, and then according to whatever the command is, there it reads the information and it gets back the whatever the information that they have to give on our command. Like if I give the command, so they have to give me the information regarding that command, right? So that will come back through there, and all of this is then my information that the command that I want to pass through the master is given through kubectl. I give my commands through kubectl to the master, then the master gives it to the nodes through the API server, and through the API server these are responding and everything works through APIs and all of the API calls are made, and then finally you get the result, right? Now let's talk about the Kubernetes objects. Now, as I've mentioned before, Kubernetes object is a record of intent. So once you create an object, Kubernetes system will constantly work to ensure that that object exists. By creating an object, you are effectively telling the Kubernetes system what you want your cluster's workload to look like. And this is your cluster desired state. So what do we mean by that is while you create an object, you tell them how you want your workload to look like on your cluster. So let's say if you have a cluster and you are defining, let's say I want 5 objects in it. I want 5 replicas. So it will create 5 replicas, and if it's not there, Kubernetes system is designed in such a way it will make sure that you always have 5 objects of that kind always available. If it is not there, then it will create more. And if it is, if by mistake, let's say if there are more than the required state, then it will delete it. So whatever you define in your record of intent, that is your object. Kubernetes will make sure you have your desired state always maintained. To work with Kubernetes object, whether to create them, to modify them, or to delete them, you'll need to use the Kubernetes API. So as we mentioned before, this is a very client server based model where it works primarily on APIs. So you make an API calls through this command line interface, which is kubectl. So when you use the kubectl command line interface, the CLI or the command line interface, which is the kubectl, it makes all the necessary calls for you, all the necessary API calls. You just give it a command. It takes your commands and makes those API calls so that you get whatever you were expecting out of it. So that is the important part of it. Then every Kubernetes object includes two nested object fields that govern an object's configurations. First is the object spec, which is basically the specifications, you can say, but object spec, and then there is object status. Now let's dig into what these object spec and object status is. So spec is just the object spec, which describes the desired state of the object, the characteristics that you want to have in your cluster. So whatever the state that you want your desired deployment or the pod to be in, you define that inside of the spec, and then in the status you describe the actual state of the object, and this is supplied and updated by the Kubernetes system. So here in the spec section, you describe the desired state for the object, the characteristics that you want for the object to have. And here in the status, you describe the actual state of the object, and is supplied and updated by the Kubernetes system. So when you use Kubernetes APIs to create these objects either directly or via the kubectl, the API request must include that information as a JSON in the request body. So JSON is another file format. If you have worked with JSON or Node.js or something like that, you create this file, which basically looks like a key value store again. It is well defined and it's pretty readable and easy to understand. So whenever you are using an API request, that must contain the information as the JSON format. So most often you provide this information to kubectl in a YAML file. So this YAML file is very similar to a JSON file, and so it is very easy for kubectl to convert that YAML file into a JSON file while making those API requests. Now, as we mentioned before, YAML file is a very important aspect when dealing with Kubernetes, because all of the things that you will be defining inside of a YAML file. So it is very important to understand how to create a YAML file and to properly make those information and configurations inside of it so that your entire Kubernetes system runs properly, right? So that's why the next thing on our agenda is introduction to YAML. So we are getting more and more closer to the more interesting stuff. So this is a pathway to reach that interesting stuff. So yeah, I know it, so far it's been very theoretical, if you will. It'll be a little more theoretical a little while longer, but this is where it begins to become on the non-theoretical end, where we can see more hands-on stuff. So if you learn about making YAMLs, we can do a lot of different things in Kubernetes, which are very interesting, and it's very much fun. So we begin by introduction to YAML. So what basically YAML is YAML is abbreviated as YAML ain't a markup language. Now that's a very funny name. Whoever thought of it, that we'll name YAML and we'll put full form of Y as YAML itself. So YAML ain't a markup language is the full form of YAML. So it is data serialization language, which is designed to be human friendly and works well with programming languages for everyday tasks. So it is a very simple looking file. The only thing you need to take care of while working with YAML file is the indentation, because it takes indentation very seriously. By indentation, I mean the spaces that you provide between the two constraints that you have, or the list form of the objects file. We will be discussing that later in this section itself. So while creating that, just take care of the spaces. I mentioned it now just before starting it, because I make those mistakes all the time, and it says that something is missing and it's not properly configuring and something like that. So please take care of the spaces when you are working with the YAML files. Now YAML includes a markup language with important construct to distinguish data-oriented language with document markup language. So the design goals and features of YAML are very straightforward. So YAML data is portable between programming languages. So you can take a YAML file from here to there. It is basically a subset of JSON file. It is mostly used for giving out configurations and information related to configurations and stuff like that. So it is a very portable kind of information that you can pass on between different programming languages. There is a very much ease and implementation, ease of the implementation and usage. So it is very easy to type up. It's not that difficult. Only thing is that the spaces thing is very important to make sure of the spaces that you are using. For that, I would recommend you to use something like a Sublime Text or something where you can get the information in properly indented form where your data is going, instead of directly writing inside of, let's say if you use sudo nano and you try to write it inside of your bash terminal. Instead of that, I'd recommend you use Sublime and then copy paste it. I found it to be much better, but something suits some people, something suit the other people, right? Moving forward, it includes data consistent data model. So it has a data model which is very data consistent. So the way you write things is very consistent and you define things in a very particular way, and that's why it is very easily readable. So if you are a human, if I show you a YAML file right away, you'd be able to tell me what is going on inside it, probably, if you know a little bit here and there. So that is how we'll be learning to create a YAML file. Although when you're working with Kubernetes, there are a lot of different things that you need to learn to define a YAML file. We'll discuss that right now itself, and we'll give you a list of things as well, of the versions and stuff like that that you need to keep in mind while creating a YAML file. So a different kind of data model works with different kinds of things. So let's say, okay, we'll give you an example, then I'll show you. So YAML is a superset of a JSON file. As I mentioned earlier, this is very similar to the JSON file. So when you're making an API call, what you basically do is you have your configurations in your YAML file. So when it is making that API call, it will convert your YAML file to a JSON file, right? So there are two types of structure inside the YAML that you need to know. First is maps and second is the list. So there are two different kinds of structures that you need to know about, because that is how you define things. There are maps and lists inside of it, right? So when we map a key to a value in YAML, it is termed as map. So if you have a key value pair, like let's say name, Intellipaat, course, Kubernetes. So this kind of thing is called mapping, where you have a key and you have a value. So you map your name as Intellipaat. So when I search for, let's say if I've created this YAML file and I have this as working, so if I just search for the name, it will give me, if I just, instead of writing name, instead of the names of the name section, if I just put Intellipaat, it will work for me. So because you have defined the name as Intellipaat. And then there is a list kind of things. Now list has an arguments inside of it. All of these arguments are started with a simple dash between them, and there is a space between the dash, which we have not mentioned here. So there is a kind of a gap between them while creating them. So as you can see an example here, the first is the argument. It asks you to sleep for 1000 seconds, and then you have the second argument, which is the message which you will be giving, which is Kubernetes test. So this is like a list format. So this is very different from the maps format, where you define something with the help of a key value pair. Inside of this, you can have multiple arguments in a list kind of manner, where it is a sequence of objects one after the other that you want to define, right? So that is how you define the list kind of things. So this is a sample YAML file. As you can see, version services, but this is not very helpful. So I will show you a real life deployment file of YAML, which we'll be using in the next module, but I'll show you right away so that you understand how important the YAML files are. So we'll switch to Sublime for a second, and so you can see I have a deployment of an Nginx here. So Nginx is basically something similar to Apache servers or Tomcat if you have used. So it helps you host things on local host for exposure. So Nginx is that. As you can see, this is right here is key value pair, which is a map, right? I've defined a name, a key, and it has a value version 1. So while creating YAML files, you have to define the API version. Some will have apps v1, some will just have v1, some will have apps beta v1. I'll give you a list of things, because not all of these support, like this has the kind deployment. Since this is a deployment, I'm defining this as a deployment. This is under this API version. So when I'm making the call, this API version has this defined inside of it. But not everything has everything inside of it, right? So if I were using, let's say, ingress, or I was creating a kind of a service or a kind of volume or a secret or whatever, this will change accordingly to that. We'll give you a list of things like that. So when you are creating these files, you can find most of them mostly online. You can just search for it. If you're looking for an Nginx deployment or something, you can find most of the YAML files online itself. But when you're creating by yourself, you need to know some rules, and it'll give you some errors also. I'll show you that also. If I just change it to v1 or something, it should give me some errors in that. So here I have metadata. Now inside of metadata, I have defined the name of the application as Nginx deployment. So if I have to call this deployment, I have to use this name, Nginx Nginx deployment. It has few labels inside of it. Now labels and specs and everything, spec we have discussed early on, right? So spec is something where you define the ideal condition of what you want your cluster to be in. So the ideal position of this deployment is to have replicas 3. So I should have 3 pods which are running this deployment, which is the Nginx deployment, right? So this Nginx should run in 3 points, which is the 3 replicas in it. So I have a selector which matches the labels of app name as the Nginx. So if I'm looking for the app name, so here the app is the Nginx, then there is the template metadata, and then there is again, I have defined another specification where I have defined the containers and what image it is pulling. So this is pulling the image of Nginx 1.15.4. So 1.15.4, it is pulling that image. You can define different images that you have created in your Docker. So let's say if I had an image name as Intellipaat rocks, so I can put that here, but with its version properly, then it will pull that image inside of that container, right? And the container port is just 80. So this is how we define a deployment or deployment YAML. So this is a YAML. I'll show you how it works also a little bit, but this is just don't take it for like that you don't understand what is going on. I'm just showing you how this YAML works. This is a deployment. We'll be covering deployments in the next future modules where we discuss it in further. This is just how you define a deployment. Now, why I was saying that you can use something like a Sublime text is because of this line. You see this line right here, it contains 2 spaces between it. So every time you have something lining on and two spaces you want, you can do it like that. So while defining a YAML file, you need to put 2 spaces between anything which is defined inside of something. So inside of metadata, I have 2 different things, right? All of these inside the metadata will be separated between 2 spaces. So if I put backspace, this is 1 and 2, right? 1, 2. 2 spaces should be there. Similarly here, this is also inside 2 spaces. Now this is 2 spaces inside of this. So while I'm defining anything inside of anything, it should be separated with 2 spaces. And when you're defining something with like a hyphen, like an argument, then it has to be 1 space. See, 1, that's it, right? So inside of an argument, between a dash and the whatever the argument that you are defining, there should be 1 space. And in the mapping, while you are mapping, you need 2 spaces in there, and you should keep a space between the key value pair. So here there will be a space. So that is something you need to take care of while defining this. I'll copy this entirely. I'll show you how it works just for the sake of it. So we'll go to so here I'll write nano, which is create to open a file. So nano, this is my deployment 1. So I'll name it as dp1.yaml, right? Inside of here, I want to paste the details of this particular YAML file. So I'll just copy it. So I'd recommend you to make something like a YAML file right here when you're typing. Just make sure of the spaces. It is very important. Now we'll go to our back here, paste it, and then we'll have a look at it. And then we'll just Control X and exit. So we'll look at it once again. So see, the spaces has been made properly. The image is defined, the container post is defined, everything is working. So my YAML file is now created. Now you can just type kubectl create -f, now the name of the file, which is dep1.yaml. Now what I'm expecting here is, since the kind is deployment, it should say that this deployment was created. So let's hit enter and see what happens. And you can see the apps nginx.deployment was created. Now if I do kubectl get pods, now I have a deployment. I should get, since I mentioned 3 replicas here, I should get 3 pods, right? So if I do, see, 3 pods of the same deployment of the nginx deployment are running. Each of these are running. You can use kubectl describe pods to see in further details about the pods. Let's look at it. So you can see in-depth details here of all the pods. Like this is the name, this is the namespace is default. So this inside of default, it has this particular IP and it is a replica set. It is controlled by the replica set and its IP, its true status and everything. You can get all the details inside if you want, using this kubectl get describe pods. So just we'll do it once again, kubectl get pods, just to show you now how this is working, right? So so here the API version was 1 kind of deployment here, and nginx deployment and whatever it is deployed here. Now You can see I've mentioned 3 replicas here. That is the reason why there are 3 different pods running of the same. All of these are the Nginx deployments of the same time. All of these have the same image and same everything, just there are 3 different instances of it running. So if I have a load balancer, if I hit the pod named Nginx, if I hit the deployment which is the Nginx deployment, I have 3 pods running in it. So when I hit it from the outside, I just hit I want the Nginx to work. I want this app to be running. Now inside that app, we have 3 replicas. Now, whatever the status of these is, the load will be distributed in a round robin fashion. And whoever is free, the data will be directed to that. That is the job that the replicas do. It helps you balance the load out. You have different replicas which are running constantly. Now, what I want to show you all is, like I was saying you that the API versions, if it is not perfectly defined, that will create a different problem. So what we'll do is we'll create another deployment file, and that should not work. So what we'll do is we'll just change this to v1, okay, and just copy it entirely, and we'll create another nano file. We'll call this, let's say, not working .yaml. This should not be working, right? We'll just paste it. We'll Control S to save it, Control X to exit. Then we'll create the same kubectl create -f, name of the file which is not working .yaml. Now this should not work. See, unable to recognize the YAML file, not working YAML, no matches for the kind deployment in v1. So this is the very important part. Let me just this is the no matches for the kind deployment in version 1. So there is no API version named version v1 which has the kind deployment specified in it. So this is very important to match the APIs with the kind and whatever the data inside of it is. If these two are not matching, your deployment will not work, or whatever it is, your service or whatever you are trying to deploy will not work. You need to have proper API versions so that you have a proper kind of thing that is working. Every different thing is defined under certain things. So you have to get that spot on in order to work. That's why the original part was working, because it was apps/v1. If we just nano it, not working.yaml, if I just write again, it was apps/v1, right? Apps/v1 or app/v1. I think it was app. And then we try again to create this file. Okay, it was probably apps. We'll change it to apps. Or we can just check it out from the previous YAML file. Oh, the Nginx deployment already exists. Now, the name of the container. So while creating this deployment, the problem is I have already specified this name, Nginx deployment. So there cannot be two different deployments with the same name, right? So if I call a deployment, if I'm just like, if I type kubectl get deployment, and then I mention the deployment name, which is Nginx deployment. Then I'm specifying a name of a deployment, and it shows me the details of that deployment, that it has 3 different pods which are running inside of it. All of them are up to date and all of them are available, and they have been created 5 minutes 34 seconds ago. The problem with creating not working YAML here is it has the same name. So you cannot have 2 different things being called from the same name, right? If I have 2 different services which have the same name, how will my system know which service to respond to? That is why your YAML file is very important. You have to define everything properly in here. So that's why we made that mistake. Now we'll go back to the nano not working.yaml. We'll just change it a little bit. Instead of Nginx deployment, we'll name it Nginx test, right? You can name it whatever you want here, and then we'll come back here, and now we'll try to deploy this YAML file again. Now you can see this is created. Now if I do kubectl get pods, I will have 6 different pods, right? Kubectl get pods. It will show me 6 different pods. 3 of the type test, because I have 3 replicas here, and 3 of the type Nginx deployment. Now what I can do here is I can change the number of replicas, and the replicas which we'll be creating will be different here. So we'll do that as well. We'll go to nano again. We have to create another one, right? So we'll copy this. We'll just copy this again. We'll create another deployment. and we'll call this just not.yaml because I don't want to type. Not.yaml I've opened. I've copied this here with Control C. I've gone back to my terminal. I've just pasted it in here. Control X, Control X. Then I'll open it again for better readability. And I have to mention here apps/v1, and the name will be Nginx deployment replica test. So we'll call it Nginx rep, and inside of replicas I'll change the number of replicas to 2. So this should create another deployment which has 2 replicas, right? So it was called not.yaml, right? So we'll just type it right here real quick. Now deployment was created, so we'll just get pods to see. As you can see, now the rep has only 2 replicas as we defined the replicas 2 in that file, right? If you see the YAML file again for not.yaml, we have replicas as 2. That is the reason why it has 2 replicas here. So you can see how important YAML is while creating anything inside of it. Although we have not learned about deployments and stuff like that here, but I wanted to show you the importance of YAML files so that when I am working in future on different YAML files, you create those YAML files with me. You type those out, even though I would be copy pasting just to save time, because if I type everything and go about it, it will take a lot of time for me to explain and a lot of time for you to watch. You can just see it and start typing so that you get better hands-on on it. Also, you can either just go and copy paste. It's your wish, totally up to you, but I'd recommend you to type it out a couple of times, right? Okay, now we can go back and move on to our next section. So there are a few additional concepts that I wanted to cover before we move on to the more interesting side of things, that is performing the hands-on. Even in YAML I said that, but I did show you a little bit of what you can do with the Kubernetes, right? So moving on, we'll be covering few concepts here so that you get a better understanding of things, and in the next module we'll be hitting the dime. Okay, so there are a few additional concepts that we must touch upon before we get into the depth of Kubernetes, namely namespaces, labels and selectors. If you remember, inside of the YAML file, we saw the labels as well as the selectors in there. There are the field selectors and there are some annotations that you should know about, right? So let's begin. With name, each object in your cluster has a name that is unique for that type of resource. Every Kubernetes object also has a UID that is unique across the whole whole cluster. So if you remember, we were using the name as deployment, and I showed you this in the hands-on section. So when we tried to make 2 things with the same name, it said like you cannot make it as Nginx deployment already existed. And when we changed the name of that, it started working again. So name is what you give to the each object in your cluster. So my deployment had the name Nginx, and it can have multiple replicas of it. It will have an extended name which will be different, but all of that will be inside of Nginx deployment, right? So that is the name. So if you create a similar deployment with the same name, it will not work for you. Then only one of the object of a given kind can have a given name at a time. So this is what I've been mentioning. I showed you last time around that you cannot do this. However, if you delete an object, you can make a new object with the same name. So if I had to delete that Nginx deployment, I could have deleted that and created a new Nginx deployment with the same name, maybe with multiple replicas or something. So a Kubernetes resource can have names up to 253 character long. So you can have up to 203 characters, but you generally don't use that much. You can use proper names for it. And then moving on, every object created over the whole lifetime of a Kubernetes cluster has a distinct UID. Now, this is a very important thing because it is intended to distinguish between the historical occurrences of similar entities. So let's say we created, I told you we can we deleted that Nginx object, right? So we could have created a new Nginx object with multiple replicas. Now, instead of 3, I would have 5 replicas. Now, what is to say how that was different from the original one? So here is when UID comes into the picture. Even though you can create new objects with the same name if you have deleted the old object before, but it will have a distinct UID. The UIDs will be different for both of these to have a distinguishing factor between the historical occurrences which in between the 2 objects that we created, right? Then next is the namespaces. Now, if you remember, while we were working with YAML files as well as when we started with talking about the namespaces. So I told you kubectl get pods -- all namespaces. Inside of that, you had different namespaces inside of it. So there's a kube system, then there is a default namespace. So we can just see that quickly right here, real quick. We'll just type kubectl So let's really quickly have a look at it. So we'll type kubectl get pods hyphen all hyphen namespaces, right? If I do that, and you can see this is the namespace, right? So inside you'll have a default namespace and under which my Nginx deployment and all of the deployments that I made during that YAML file introduction, these are inside the namespace, which is default. And then there is kube system namespace, inside of which there are pre-created pods in there, right? So these are all the pods which are running inside of different namespaces. Now this is done because the namespace are the ways to divide cluster resource between multiple clusters, and Kubernetes supports multiple virtual clusters backed by the same physical cluster. These virtual clusters are known as namespaces. So physically we have a lot of clusters, but behind that also we have virtual clusters, and namespaces are a way to define those clusters. So inside one namespace, which is default, I deployed all of my deployments which I created. They go under the namespace default. Then there are few pods which are already running inside of kube-system. That is another namespace. If I define more namespaces, I will have more namespaces described inside of it, right? So namespaces are intended for use in environments with many users spread across multiple teams or multiple projects. For clusters with few to tens of users, you should not think about creating a namespace because it's not that important. But if you have a giant team, let's say 100 people are working on the same thing, then that is the point you will be needing to define the namespaces, because it is good for creating that differentiation between the virtual clusters, right? Then namespaces provide a scope for names. Name of the resources need to be unique within a namespace. As we were saying, the names that we defined inside of a namespace, two things cannot have the same name, right? But across namespaces, you can have like different names. So what we meant here is the name of the resources need to be unique within a namespace, but not across namespaces. I can have Nginx deployment, only one kind of Nginx deployment in the namespace default. Let's say if I had to create another Nginx deployment with the same name, the one way I can do that is either I have to delete the old object and create a new one in the same namespace, or I can change the namespace and create it somewhere else. That is the way it can work. Namespaces cannot be nested inside one another, and each Kubernetes resource can only be in one namespace. So that is another very important fact. Then coming on to labels and selectors. Labels are key value pairs that are attached to objects such as pods. So while creating the YAML file, you must have seen that I've shown you the labels and the selectors inside of the file. We can have a quick glance at it real quickly. Right here, you can see labels, and this is the selectors and match labels we have mentioned here. So this is, you generally define it for a pod. So the replicas are defined for my pods right here, right? So coming back to the slides. So this is generally created for things such as pods, and these are intended to specify the identifying attributes of an object that are meaningful and relevant to the users, but do not directly imply semantics to the core system. So it is usually for identification purposes, and these are the identities, these values which we are identifying are mostly, let's say, these are mostly concerned with the user. Like the users are concerned with these, not necessarily that it impacts the system in any way or impacts the semantics of the system in any way. So unlike names and UIDs, labels do not provide uniqueness whatsoever. In general, we may expect many objects to carry the same labels. You can define labels inside of metadata as labels like this. I've showed you in the YAML file before how you can define that as well. Through a label selector, the client/the user can identify a set of objects. The label selector is the core grouping primitive in Kubernetes. The API currently supports two types of selectors. One is the equality-based selector and the other is the set-based selector. We'll discuss that now. So equality or inequality based requirements allow filtering by label key and values. These generally what they do is they'll be matching the objects that must satisfy all the label constraints, though they may have additional labels as well. So when I'm using the equality based selector, what I'm looking for is the objects which will be having all of the defined labels that I want. So let's say if I want the label as label 1, label 1, label 2. So it will get all the objects that will have label 1 and label 2, but that can have label 3 and label 4 as well. So it will get all the objects that have label 1 and label 2, but it can have more. But let's say if I have an object that has label 1 but not label 2 but label 3 and label 4, and I'm looking for label 1 and label 2, that object will not be fetched. It will only fetch those objects which have label 1 and label 2. right? Then there is a set based labels. This basically these requirements allow filtering the keys according to the set values. So you can have a set of values that you are looking for. 3 kinds of operators are supported in this: in, not in, and exist. Only the key identifier, if something exists in a label or not, if something is in the label or not, if something is not in the label or not. That is the set based requirement. Moving on to field selectors. Field selectors let you select Kubernetes resource based on the value of one or more resource fields. So field selectors are essentially resource filters. By default, no selectors / filters are applied. So if you do not define it, by default there are no selectors or filters applied, meaning that all of the resources of the specified type are selected. If you specify a type of resource, everything will be selected if you do not define a field selector, right? So you have to define it. By default, everything will come inside of it. Finally, the last concept on our hand here is annotations. Now, annotations are not used to identify or select objects as labels do, as I mentioned earlier. But annotations can be used to define metadata. So it can be large or small, it can be structured or unstructured, and CAD includes characters that are not permitted by labels. General use of annotations is to define the build release or something like that. You can have this information somewhere in the backend directory, you can refetch, but some people choose to define these metadata in the form of annotations. So that is the actual use of the annotations.
Just a quick info, guys. Intellipaat does provide end-to-end training on Kubernetes. So if you're interested, you can check out the course details given in the description below. So this brings us to the end of this session. If you have any queries, please leave a comment down below and we'll reach out to you immediately. Thank you for watching, guys.